Morning, everyone. My name is Xinqiang Ding. I'm from Tufts University. First, I want to thank the organizer for the opportunity to share my research. So today, I'm going to mainly talk about new method which can improve energy estimate for free, almost for free. All right. So I started my independent group about 2 years ago. So I want to use this opportunity to introduce some of the research in my group. Of course, energy calculation methods is a big part of it. Specifically, we're focused on developing new methods that can efficiently compute absolute binding for energy. And we have heard several talks about the potential of using absolute binding for energy for virtual screening if we can do it more efficiently. The second part is that we want to incorporate prior knowledges into energy calculation using Bayesian methods. So in this talk, I'm going to mostly focus on this part. So besides the energy calculation, we also do some enhanced sampling and also force field development. So we mostly focus on in-place solvent model for both structured and disordered proteins. So our main approach in my group is to combine techniques developing molecular simulation and machine learning. We use a lot of Bayesian inference, probabilistic generative model, and we also use many sampling and learning algorithms that developed in machine learning. So I think there are many common techniques that are developed in molecular simulation and machine learning. So we try to borrow methods from machine learning and see how they work for our molecular system. Right? Okay, let's dive into the main topic of for today. So maybe let me first explain what I mean by improving energy estimate for free. So I'm sure everyone in this room are familiar with the two steps we usually take to compute energy difference among multiple states. So usually, when we identify the multiple states, we run, molecular dynamic simulation or Monte Carlo sampling to sample configurations from all the states. And this step is usually quite expensive, requires many GPU hours. After that, we can compute energy using the sampled configurations. I think the current standard protocol is to use the BayesMBAR methods to get the energy using the sampled configurations. So compare with the first step, the second step is very fast. It usually takes only a few CPU minutes or a few GPU seconds. Okay. So because the second step is so fast, we ask the question that, is it possible to improve the accuracy of energy estimate by investing just a little bit more computation in the second step without running more simulations, without running longer simulations? This seems impossible, right? Because there's a theorem in energy calculation called there's no free lunch. Because if we are not running longer simulations, but we want to get better energy estimate, then we have to get the information from somewhere else. So where could the information come from if it is not from longer or more simulations? Any guess? Okay. We can actually, before we even running simulations, we have some prior knowledge about the energy. So I usually classify prior knowledge into two types. The first type is system specific. Maybe you have worked on this system for a long time. Maybe you have some experimental data that can give you a prior knowledge about the value of the energy. Maybe you have some prediction from some machine learning methods that can give you some prior knowledge about what the value could be. There's another type of prior knowledge, which I will call general prior knowledge. Those kind of prior knowledge applies to all systems. Okay, they usually come from physical constraints, physical laws, or the statistical property of energy that are applicable for many systems. Okay? So in this talk, I'm mostly focused on this general prior knowledge and how what they are and how we can incorporate into energy estimate in order to get a better estimate. So let's give you an example about general prior knowledge of energy. So this is the first example. This is simple. We all learned from thermodynamic course, right? Energy is a state function, meaning that if I have 3 thermodynamic states, A, B, and C, and I have 3 free energy difference among the 3 states. Now I have a thermodynamic cycle. And because free energy is a state function, then the sum of the 3 free energy difference has to be equal to 0, exactly. Right? And we know this should hold for all the system before we do any calculation. So I will refer this as the cycle consistent condition. So this one is easy. This is a general prior knowledge. Let's look at another general prior knowledge about free energy. So this is a little bit subtle. So in order to prove that this is indeed general prior knowledge that you know of, so let me ask you a question. So you are giving a test, and the test is, there is a physical process described by one collective coordinate, which is shown on the x-axis. You are given 2 choices for the free energy profile along the collective coordinate. Which one do you think is more likely to be the correct free energy profile along this physical process? The one on the right. Okay, can someone see why? More continuous, more smooth. Exactly, thank you. We know that usually for a physical process, for most of them, the free energy profile are usually a smooth function along collective coordinate, right? So this is definitely has higher probability being the true free energy profile than this one. Now, we have at least 2 types of general prior knowledges. We might have, some other more. Then the question becomes, how can we incorporate those general prior knowledge into free energy estimate? In order to do that, we develop a method called BayesMBAR. So incorporating prior knowledge into your inference is not a new task. We don't want to reinvent the wheel because there is already a whole field devoted to this question, which is Bayesian inference. So it's a principled way of combining prior knowledge with data for inference, right? So let's assume that we are interested in inferring the parameter called theta. So in Bayesian inference, what we do is first, we specify a prior distribution pi of theta that encodes our prior knowledge about theta before we observe any data. Then usually this prior knowledge is a bit vague, right? It's probably a broad distribution. You don't know exactly what's the value of theta. In order to get a better estimate, you go out, you collect data. Okay? Once you collect data D, then you make the likelihood function, which measures the probability that you will observe your data giving a value of theta. So this will include the information from the data. Then we can turn on then we can use the Bayes theorem to derive the posterior distribution, which is what is the probability on the parameter theta given our condition on our already observed data D. So, and this posterior distribution is proportional to the product of the prior and the likelihood function. So the posterior distribution combines the information from the prior distribution from our prior knowledge with the data. So once we have the prior distribution, our inference is essentially done because we can do the following up many tasks based on the posterior distribution. So essentially, we can do inference once we have this posterior distribution. So this is a very, very general framework, and we can view free energy estimate as a Bayesian inference. So specifically, our aim here is to infer the free energy of many thermodynamic states, let's say alchemical states. So first of all, we define a prior distribution that can encode our prior knowledge. Then we go to collect the data. So the way we collect data in alchemical free energy calculation is just running simulations of all the states. Now we define the likelihood function. So we essentially measure what's the probability of observing the data from simulation given the free energy. Then we can calculate the posterior distribution. Okay, let's see how it works. You see, in order to carry out this framework, we really have to define two things. One is the prior distribution, the other is the likelihood function. So let's look at the prior first. As I said, Bayesian inference is a very general framework. It can incorporate prior knowledge, but you can choose to not incorporate any prior knowledge. In that case, what you can do is you just specify the prior distribution is as a uniform prior distribution, meaning that all possible value of the phrenology has equal probability. You can choose not to encode any prior knowledge. Let's say if we want to encode this cycle consistent condition, how can we build the prior distribution? This is also quite easy to do. What we can do is we can define the prior distribution as a uniform distribution in the subspace of phrenology defined by the constraint, meaning that all values of phrenology that satisfy this condition has equal probability density. If the value does not satisfy the condition, the probability density is equal to 0. So this prior distribution, include this condition exactly. How about the other one? The other one is the prior knowledge is phrenology profile are usually smooth functions. Well, in Bayesian inference, there's already a prior that can encode a smooth function, which is a Gaussian process prior. So here on the right here, I'm showing you a Gaussian process is a distribution, probability distribution on functions. So you sample, if you do sample for each sample, you sample a function instead of just one scalar value. So on the right here, I'm showing you 5 samples from a Gaussian process. As you can see, each one of them is a smooth function. Okay? In contrast, if you don't have Gaussian process, if you assume each value of f are from a uniform distribution, the profile you get will be something like this. Okay? It's no longer a smooth function. Okay, that's the prior distribution. The other ingredient is the likelihood function. How do we define the likelihood function? Measure the probability of observing data from simulation given phrenology. So conventional wisdom, or intuitively, we will come up with this conventional likelihood, which is essentially the Boltzmann distribution. So we observe, let's see, a confirmation of X from state I, and the probability of this confirmation given the phrenology is equal to this Boltzmann distribution. Unfortunately, this will not work because this likelihood actually does not contain information on the phrenology. Why? Because you can change the value of the phrenology without changing the relative weight of all the configurations. You see, if you use this likelihood, the simulation data actually does not give you more actual information about the phrenology. A better likelihood is this reverse logistic regression likelihood, which was proposed in the 90s in statistics. So it is a little bit not very intuitive. So instead of viewing the confirmations from simulation as data, you view the state index of that confirmation as data. Assume that from state I sample confirmation XIK is the case confirmation. Instead of you viewing this as data, we assign for each confirmation a state index. Because this confirmation is from state I, then this YIK will be equal to I. Okay. Now you ask the question, what is the probability that this configuration actually comes from state I compared to all the other states? Because this confirmation could also be sampled from other states. In order to do that, you calculate this you calculate this probability. As you can see here, this is very similar to logistic regression, where you try to predict the state index given the confirmation. So that's why it's called reverse logistic likelihood. Now we can put everything together. We know how to define the prior distribution. We know which likelihood function we want to use. Now we can divide the posterior distribution as a product, as a prior, and as a likelihood. So once we have the prior distribution, we can do inference on phrenology. For example, we can, let's say, I just want to get a point estimate, the best estimate on the point estimate on the phrenology. What I can do is I can use the posterior mode as estimate for the phrenology. I can also use the posterior mean as a phrenology estimate, right? And it's very naturally, we can also estimate the uncertainty of our estimate using the posterior standard deviation. Right? Because you have a distribution, you can easily calculate its mean, its standard deviation. Okay, so here, so this will be the whole thing. I just call it BayesMBAR. Why? There is MBAR in the title, right? Okay, that's later. Okay, so let me give you some example about posterior distribution. So here are two examples. On the left here, I try to calculate phrenology between two states. Okay, so this, because there are only two states, there's only one third there's only one phrenology difference, and this will be the posterior distribution of the phrenology difference. So we can also do, we can also do calculate phrenology for any number of states. Here is phrenology difference among three states, because there are three states. There are 2 degrees of freedom. The phrenology difference between states 1 and 2 and 1 and 3. So here the contour shows the posterior density of phrenology. Okay. Each point here is just a sample. Okay, that's a lot of Bayesian statistics, Bayesian inference. So, but the question is, why bother? What do we get from this Bayesian framework? So first of all, theoretically is a very theoretically pleasant method, because it's actually generalized MBAR, meaning that we can view MBAR as a special case of BayesMBAR, meaning that if we choose the prior distribution as a uniform distribution and use the mode of the posterior distribution as our estimate, then this estimate is equivalent to the MBAR result. But it actually, BayesMBAR actually brings something more, which is that for uncertainty estimate in BayesMBAR, I'm sure everyone of you is familiar that MBAR can not only give you an estimate but also give you an uncertainty. So in MBAR, one way to get the uncertainty is to use the asymptotic analysis. So what this does is you go to the mode of the posterior distribution, you look at the curvature, and you approximate this posterior using a Gaussian distribution, and use the standard deviation of this Gaussian distribution as the uncertainty. But because, as I shown here, because you only use the local curvature information, usually the asymptotic distribution overestimate the uncertainty. So in BayesMBAR, because we have access to this full posterior distribution, we can get this. We can get a better uncertainty estimate. Here is some results. Here is estimating phrenology difference between two states. So the x-axis is the number of samples we use to calculate the phrenology difference. The black line is the reference. The y-axis is the uncertainty. The black line is the reference value, which is the value we want to get. As you can see, MBAR overestimates the uncertainty when the number of samples is small. And BayesMBAR also overestimates the true uncertainty, but it's more closer to the reference. So that is when we use the uniform distribution as a prior. What if we use other priors? For example, what if we use the smoothness of the phrenology profile? Does it improve the phrenology estimate? So here I try to use alchemical method to calculate hydration phrenology of phenol and using the Gaussian process prior. The x-axis is number of samples we use to calculate phrenology, y-axis is RMSE. If you use the uniform prior, this will be the RMSE. If you use the Gaussian prior, it will be the RMSE. So there are error bars. I didn't show it here. The difference are significant. As you can see, especially with the number of samples is small, the Gaussian prior can indeed improve the phrenology estimate. How about the other prior, which is the cycle consistent condition? So here I apply it onto for calculating relative binding phrenology on this protein, and this is the scaffold. And I made this perturbation graph with cycles 1, 2, and 3, right? So we try to consider all the cycles as encode all the cycle information into the prior distribution. So there are two other methods that are developed for this purpose. One is called a cycle closure correction. The other called MBARnet. Also kind of use the cycle information to improve phrenology estimate. So here is the result. Here is MRC in the water phase. This is MRC of free energy in the protein phase. This is the length of the trajectory we use to calculate the free energy. This is RMSE. As you can see, if you just use M-bar on each edge individually, this will be the accumulated RMSE. If you use M-bar, after you get the M-bar result, you use the cycle closure correction, it can get you a lower RMSE. Okay, and this is the BayesMBAR. BayesMBAR is we couple all M-bar all together in this perturbation graph. So at the end, you can do the you can after you run your simulation, you put all your energy value into BayesMBAR. BayesMBAR will give you the free energy for all the edges that automatically satisfy all the cycle closure condition. As you can see, BayesMBAR we can do better than this if you do this separately because of the probabilistic framework. All right, so how to use it is the code is here. We also have a documentation page. It's very similar to PyMBAR. Essentially, you just give it a similar input if you want to use the uniform prior. If you want to use Gaussian prior, it's more involved. You have to specify kernels, what is the collective variable. If you want to use the consistent cycle consistent condition, it's also very easy. You give it all the energy, all the energies that similarly to what you give to PyMBAR, but you also give it the topology of the graph structure. It will consider all the cycles for you. All right, I think my time is up. So here is the summary. The future work here, I only talk about using general prior knowledge. I'm sure, there's system prior knowledge in specific project or from machine learning methods. We are working on that. I think the difficulty there is when you try to combine prediction from machine learning with simulation is that the machine learning not only need to give a prediction, but also need to give a confidence of the prediction. So if the machine learning want to make a wrong prediction with low confidence, that's fine. So the worst situation is the machine learning make a wrong prediction with high confidence. That will mess everything up. Okay, thank you.
All right, we've got time for a couple questions.
So the actual smoothness actually is also learned from the data. So in the Gaussian kernel, there are some parameters. One is there are some parameters that can control how smooth of the final profile. And in order during the optimization, the BayesMBAR also optimize those parameters. So how smoothness will be determined by the data as well. Right. Yes, the great question. So usually for bootstrapping, it's actually included in the paper. It sometimes underestimates the uncertainty just a little bit. It's actually much better than the asymptotic analysis. I think we don't want to use asymptotic analysis. Yes, slightly underestimate the true uncertainty. I would argue slightly overestimate the uncertainty probably is better because to convince you need to run longer simulation. The underestimate uncertainty will have the risk that you have higher confidence than you actually have.
All right, that's all the time we have for questions. Let's thank Xinqiang Ding.